Today we are going to talk about small signal amplifiers. So let's start with a microphone. And our goal is to amplify the tiny signal that comes from this microphone and eventually put that signal into a power amplifier that can run a loudspeaker. So what we have is basically a public address system or PA system, and obviously it works at audio frequencies. This could just as easily be a radio receiving antenna, and then it would work at radio frequencies. But a PA system is a good circuit to analyze to understand how basic amplifiers work. So let's take a look at this microphone and see what it does and see what we have to do to make the signal useful. If we imagine my pin as a microphone, inside the head is a plastic diaphragm, and attached to that is a spool with a coil of copper wire around it. And that is suspended in a magnetic field so that it is free to move back and forth. And when I talk, pressure waves hit that diaphragm and cause it to vibrate. When that diaphragm is moving away from me, it pushes the coil into the magnetic field, and as we know, when you push a piece of wire into a magnetic field, it induces a current in that wire. So we get an electrical current that flows one direction depending on how the microphone's oriented. Then when that diaphragm moves towards me, it pulls that coil the opposite way through that magnetic field and induces a current to flow in the opposite direction. So when the diaphragm is moving towards me, the current goes one way. When the diaphragm is moving away from me, the current moves the opposite direction. But there's no circuit here for that current to flow, so actually what we get is voltage. So when the current is trying to move clockwise, we get a voltage that's positive to negative, and then when the current is moving counterclockwise, we get a voltage that is negative to positive. This is going to be a pretty tiny voltage, so let's assume that this microphone produces 20 millivolts peak to peak, which means that when we have 0 volts, we would have this when there's no sound coming to the microphone. When that diaphragm is moving away from me, I'm going to get a voltage that goes up and then peaks at, when we have the diaphragm at the maximum acceleration, it's going to peak at positive 10 millivolts. And when that diaphragm moves towards me, it's going to peak at minus 10 millivolts. So we have a total of 20 millivolts peak to peak. Now, my voice is pretty complex and it's going to be hard to analyze. So let's just assume that I can produce a sine wave, and this is what we get, a nice clean sine wave that just repeats itself. So as that diaphragm vibrates back and forth, we get a wave that peaks at positive 10 and minus 10 millivolts. And it just, as long as that diaphragm is vibrating, we get this sine wave off of it. Okay, so now that we've established that, we need to amplify that so that we can drive a power amplifier. So how are we going to do that? First of all, we need to increase the voltage. We only have 20 millivolts peak to peak. So how are we going to increase that voltage? Well, the first thing you might think of is a transformer. Okay, so let's put that on a transformer, a nice step-up transformer, and step up that voltage. As a matter of fact, some systems do use transformers on microphones, but not the way you think. It does something a little different. Let's see if we just try to use this as a step-up transformer. So we have 20 millivolts peak to peak here. Over here, let's say we step it up 10 times. 40 millivolts. Great, we've got some increase. We could add some more coils over here and get it to increase even more. But what happens? Well, eventually we need to produce more power. Are we going to increase the power going across a transformer? And the answer to that is no. We cannot increase our power. So if our voltage goes up, something else has to give. How do we calculate the power? Well, in this case, voltage times current. So if our voltage goes up, but the power stays the same, our current has to go down. And so if we have 1 microamp here, we're down to 0.5 microamps here. So our power stayed the same. We need to increase the power to drive that speaker. Remember, the ultimate goal of most electronic systems is to produce power. Power is produced when you have electromagnetic radiation or mechanical motion or heat. Our goal is to produce a lot of mechanical motion, to move air and thus have a louder sound than we started with. So we need to increase our power. So stepping up the voltage with a transformer, we're not going to increase our power. Our power is going to stay the same. So we have to find something else to do. So what can we do to increase our voltage and at the same time increase our power? And that's going to be a transistor. So what we're going to do is run this microphone into an NPN transistor. So there it is, going from the base to the emitter of an NPN transistor. And so we have a circuit through here. And as we know, what does a transistor do? Well, if we look at it, not looking at anything else, assuming I have a power source out here somewhere, if I have a small current flowing into the base, I get a considerably larger current flowing into the collector. And of course, those both go into the emitter. And we'll talk about what happens with that later on. So I get a tiny current into the base and a bigger current into the collector. And to get that current, what I'm going to do is I'm going to need some kind of a power source. So let's put a battery over here. And so small current into the base, big current into the collector. But in preparing to run our power amplifier, we need to amplify our voltage. So we need to make this a voltage amplifier. What does that mean? Well, what's the difference between a voltage amplifier and a current amplifier? For a current amplifier, we basically want changes in our base current to cause proportional changes in our collector current. What we need to do is design this so that changes in our base voltage cause proportional changes somewhere else. And so what we're going to do is put a resistor right here. So what does that do for us? Well, let's examine what's going to happen at that resistor just by itself to see what it's going to do. Let's eliminate the rest of the circuit so we don't have any confusion. We're just going to have that resistor all by itself. And let's assume that was a 10-volt battery, so there's plus 10 volts. And somewhere else there's other circuitry down here. So this is to the positive side of the battery, and there's other circuitry down here causing things to happen, but we just want to see what's going to happen at this resistor. So somewhere we have a ground, but we don't know what's between. We just know that our current is going to change through this resistor. Let's assume that right now we have an open circuit here, so there's no current flowing. And let's just say that this is a 1K resistor. Okay, 10 volts, 1K, no current. What's the voltage going to be across this resistor? Well, the rule is to get any voltage difference between here and here, we must have current. So what do you need to get a voltage difference? You have to have resistance and current. Do we have any current flowing through here? No, we've established that this is an open circuit right now, so there's no current flowing, which means that the voltage here will be the same as the voltage here. Remember my demonstration with the soda straw. Right now, we just have an open straw. I'm going to pinch this down, which represents the resistor. So this is our wire. The pinch represents the resistance. Right now, we have 15 pounds per square inch on both sides of this. And even if I block this off, well, since there's no current flowing through, and there's nothing to prevent molecules from freely flowing from one side to the other, this is not completely pinched off. There's a little room for air to flow between. I will have the same pressure on both sides. So I can pinch this off till the cows come home, and it's not going to change the pressure. Now I'm going to suck on it. Well, what happens? Remember that the negative side of a battery is like the suction side of a vacuum cleaner. We usually think of the positive side as pushing electrons. Don't forget that the negative side is like a vacuum, sucking them back the other way. So it's acting just like me sucking on this soda straw. So if I start sucking on this, it's going to cause a drop in pressure on the side that I'm sucking from. So this voltage is going to go to something lower. And the harder I suck on it, the lower that voltage is going to go. So as I increase my current, this voltage goes lower. Once again, think of it like a vacuum cleaner where I have a suction side over here that's sucking the voltage down on this side. So when we get current flowing through here, we get a lower voltage, and the more current we get, the lower this voltage goes. How low can it go? Well, if I have no resistance between here and ground, remember this is the positive side of the battery, this is the negative side of the battery. So if I have no resistance, I'm going to have 10 volts on this side, 0 volts on that side. So at that point, I'm going to have my maximum current, which is 10 milliamps, at which point I will have 10 volts across this 1K resistor. So once again, we don't know what's going on here, but something is causing the current to change. When there's 0 current, 10 volts. As I increase the current, this voltage will go down, and at my maximum current, in this case of 10 milliamps, I get 0 volts. Okay, so that's what's going on at that resistor. So let's go back to our complete circuit. And so now we know that as our current increases from the base to the emitter, we get a bigger current through this. So more current here means even more current here. And if we take this as our output, now what's going to happen to the voltage at this collector? When there's no current, let's make this a 10 volt battery. So remember, there's going to be 10 volts here, 0 volts here, there's our ground. So now when there's no current, 10 volts. When we get our maximum current, which is going to be 10 milliamps, we get 0 volts. So the greater current, the lower the voltage. So as our current goes up, this voltage goes down. And if we set this up right, we can get it so that the voltage here is proportional to the voltage there. Okay, so there's our voltage amplifier. Now let's look at it in operation. So what do we have going into the base of this transistor? We have a nice little sine wave, because we said so, that's going to positive 10 millivolts and to negative 10 millivolts. And that's going to go into the transistor. It's going to cause some current to flow from the base to the emitter. And have you seen the problem yet? How much voltage is it going to take between this base and the emitter before that transistor starts to really function? Minimum, absolute minimum, is going to be 0.5 volts if this is a silicon transistor. So that's not even going to get this to start working. And really, we want to get this above about 0.7 volts. Remember the way the diode curve works is that if we have our current on our vertical axis and our voltage on our horizontal axis, and we put about 0.5 volts there, we get nothing, no current until about 0.5 volts. Then we get a curve, and it starts to straighten out at about 0.7 volts. So we want to get the transistor operating in this area here. We don't want it operating on this curve, because that means that our collector voltage will not be proportional to our base voltage. A tiny change in base voltage will not produce a proportional change in the collector voltage. We want basically to where if we double our base voltage, we double our collector voltage. So this means that if we operate in this area, well, changes in voltage here don't make much change in current, but a change in voltage here makes a big change in current. And if we're operating in there, it's going to be like, well, it's going to cause severe distortion. We've got to get out of this region here. So we really want to get this up to around 0.7 volts and operate in that area there. So that's our problem at this point. Let's remove some of our clutter here. And so what are we going to do here to increase our voltage on the base to about 0.7 of a volt? Well, let's run a resistor down there from our power source. And what we want to do is carefully select this resistor so we get just the right current that gets this up to about 0.7 volts. And now changes from the microphone are going to cause changes over here. But there's a slight problem here. Of course, we're going to get current going this way, but we're also going to get current going through the microphone, especially if this is a dynamic microphone, because what is it? It's a coil of wire in a magnetic field. So what we're going to get is an electric current going through the coil. What happens when you put a current through a coil of wire that's in a magnetic field? Well, it's going to cause a magnetic field around that coil. It's going to interact with the permanent magnet, and it's going to cause that diaphragm to move. So it's going to actually physically move the diaphragm in the microphone. Even a crystal microphone, which would act more like a capacitor, the voltage across it would cause it to distort. So we don't want any voltage or current going through the microphone. So what are we going to do? How are we going to block that current? And this is called the biasing current. We are biasing this transistor. How are we going to prevent that DC bias current from going through the microphone? Do we have a device that can block the direct current from going to the microphone, but yet allow the alternating current from the microphone to go to the rest of the circuit? And what device is that? It's a capacitor. What's the mantra for a capacitor? It blocks DC, but passes AC. So let's put a capacitor here. How big of a capacitor? We want the capacitive reactance to be low enough that it acts like a short circuit to our alternating current. I don't want to get too deep into the calculations of this. That's beyond the scope of this lecture. But we want this to have a large enough capacitance so that at the frequencies we're working at, it looks like a short circuit. Remember, the bigger the capacitor, the smaller the capacitive reactance. So a bigger capacitor looks more and more like a short circuit to our alternating current. So now our DC is blocked, but our alternating current from our microphone can go right through. Okay, so now we're getting to a workable circuit here. So we choose this resistor, and it's going to be highly dependent on the characteristics of the transistor. So I can't really give you a formula of how to choose this. To tell you the truth, I'd probably do it trial and error, get a variable resistor and play with it till I get it just right. We want to get our current through here to approximately 0.7 volts. And what's going to happen is we have over here our sine wave going to plus 10 millivolts and minus 10 millivolts. Remember, this acts like a short circuit to the alternating current. So if this goes up by 10 millivolts, this voltage here will also go up by 10 millivolts. So if this was 0.7 volts, when this reaches the peak, this will be 0.71 volts. And likewise, when this goes down to the minus peak, it's going to pull this voltage down by 10 millivolts. So when we get to our minus 10 millivolts here, it's going to pull this one down to 0.69 volts. So as this goes up and down by 10 millivolts, this also goes up and down by 10 millivolts. So we have 20 millivolts peak to peak here and 20 millivolts peak to peak here. The only difference is this is centered on 0 volts and this is centered on 0.7 volts. But the wave is going up and down by 20 millivolts either side. So we get our changes in voltage at the base that we amplify to become changes in voltage at the collector. Now let's clean this up so we don't have too much clutter up here. So there's our basic circuit. And so what's going to happen here? As this voltage goes up, the current through here increases. As this voltage goes down, the current from the base to the emitter decreases. So as this current increases, this current gets larger. Remember what happens as this current goes up? This voltage goes down. As this current goes down, this current goes down, and therefore this voltage goes up. When we have more current, it means that this battery is sucking harder, and it's going to pull this voltage down. So as my current increases here, my voltage goes down here. As my current decreases, my voltage goes up. So basically what's going to happen is I have my voltage at my base. There's my 0 volts. And as that goes up, current increases, this current increases, this voltage goes down. As this goes down, this voltage goes up. Look what's happening. As this voltage goes up, this voltage goes down. As this voltage goes down, this voltage goes up. So we get a 180-degree phase reversal from the input to the output. That's no big deal. If it's a problem, there are ways to deal with that, but usually it's no problem. But this is going to be a bigger voltage than this voltage because of the changes in current. Okay, let's look at some of the problems we might have. Now remember that over here, when we had zero current flowing through the transistor and we had zero current through the resistor, what was our voltage at this point? Remember that when there's no current, there's no voltage difference. So if it's 10 volts here, it's 10 volts here. Let's move this battery, make some room for a little chart over here. In fact, let's get rid of the battery entirely. That gives us a little room to draw over here. Remember, these just connect to the positive side of the battery. The grounds connect to the negative side of the battery. Now remember what happens over here. When there's no current flowing through this transistor, we have no current flowing through the collector resistor, and therefore what's the voltage on the output? Remember, no current, no voltage difference, 10 volts here, 10 volts here. So that's our lower limit on our current. We cannot allow our current to fall to zero. Otherwise, when our wave comes out, it's going to top out at 10 volts and we'll get what's called clipping. It'll flatten off the top of the wave. So we have to keep our wave below 10 volts. Likewise, what happens when we get our maximum current? The maximum current, remember, was 10 milliamps, because at 10 milliamps we get 10 volts across our 1K resistor. We can't get any more. We have to start with 10. We can't lose more than 10. So when this reaches 10 milliamps, this is going to be 0 volts. And if we put that down here, that gives us a lower limit. We cannot allow this current to attempt to exceed 10 milliamps because that will cause us to go down below 0 volts and will flatten out the bottom. So we have a practical limit where we need to keep our output voltage from going above 10 volts or attempting to go above 10 volts or attempting to go below 0 volts. So likewise, we cannot allow this current to go to 0 and we cannot allow it to hit 10 milliamps. Now, to make sure this is symmetrical, what do we want to do at this voltage when we have 0 volts on the microphone? Let's say there's no input, so we have a steady 0 volts, which means this is going to be, assuming everything's biased right, 0.7 volts. What do we want our voltage to be here so that we can still amplify our wave? So we're going up 10 millivolts, down 10 millivolts. We want to be able to go up and down an even amount, plus 10 millivolts, minus 10 millivolts. We want this to be able to go up almost to 10 volts and down almost to 0 volts. So our middle voltage is going to be right there. So when there's no signal coming in, there's our voltage, just sitting there somewhere in the middle. And when a signal comes in, what's going to happen? It's going to go up and down. So what voltage do we want that to be? We want to set this up so that when there's no input, this is going to be half of our power supply voltage. So in this case with 10 volts, that's going to be positive 5 volts. So now what we need to do is select these components, the transistor, the base bias resistor, and the collector resistor. We want to choose those such that we get about 0.7 volts on the base, and with our quiescent current, meaning quiescent meaning no input, and it's just sitting there, we want to set this at about plus 5 volts. So it's a very careful dance between the HFE of the transistor, how much amplification does it have, the base bias, and the collector resistor to get this just right. And I'm not doing any calculations on this because, well, if you really want to do that, there are books that can show you the formulas. And to tell you the truth, you're probably going to end up doing it by trial and error anyway. But let's say we've got it working and we've picked just the right resistor, and I picked 1K here. Might end up being a slightly different resistor, because another thing to look at is how much amplification we get. And as this resistor increases, what's going to happen to this voltage? the point here is, the larger I make this resistor, the more voltage gain I get. So once again, it's a very careful balancing of what's the size of this resistor, what's the size of this resistor, what's the HFE of the transistor. And to tell you the truth, you're going to have to do this by trial and error because there's so much interdependency there, but we can finally get an amplifier that's going to amplify our signal just the right amount. And that's the basics of a Class A small signal amplifier. Class A meaning that it amplifies the entire signal, both the positive and negative sides. So a quick review on what we did here. We increased the base current to bring this voltage up to where the voltage coming from the microphone would push this up and down in a region where the transistor will operate fairly linearly. This capacitor keeps DC currents from going to the microphone but allows AC currents to come through. As this voltage goes up and down, this voltage will go up and down the same amount. So we have an offset here. This is centered on 0 volts. This is centered on 0.7 volts. Either side goes up and down 20 millivolts. As this goes up, we get an increase in current. Increase in current, what happens? Our voltage goes down. How much does it go down? It depends on how much current and how big this resistor is. The bigger this resistor is, the more it goes down. So we want to increase the voltage gain. We increase the size of this resistor. But once we get it all balanced out to do just what we want, we can get a nice amplifier that takes our small signal here and gives us a much bigger signal here. Only difference is I really should draw this reversed, because as this voltage goes up, this voltage goes down. Once again, it's centered on 5 volts. So as this voltage goes up, this voltage goes down, 180-degree phase shift. But if we carefully match all of these resistors to the HFE of this transistor, we can get just the right voltage here so that when there's no signal, this sits at 5 volts. When the signal comes in, it doesn't go above 10 volts, doesn't go down below 0 volts, and we have a nice Class A small signal amplifier. Except it can't work. The reason is that everything is so dependent on the HFE of this transistor, which changes with temperature, changes with our current, changes with our base voltage, changes with our collector voltage. It's so interdependent on so many things that it is so fiddly that you can't really get this to work. And on top of that, it has way too much gain. This is going to be a huge resistor, like 1.5 megohms or bigger, to get this to be just the right amount of current, to get just the right voltage here, get just the right voltage there. This one's not so critical. But the real problem is going to be this transistor right here, because even if I buy transistors from the same batch, from the same manufacturer, they're all going to have slight differences in HFE, which is going to throw my voltages all off. And even the temperature is going to change that. And because the HFE of the transistor is dependent on other factors, I'm going to get severe distortion over here. It just doesn't work. So even though you might see this in textbooks, well, here's a way to make a Class A small signal amplifier. What's the next thing they do? Is they say, well, here's a way to make it a little better. One thing we can do to improve this amplifier is to move this resistor to here. And that gives us a little bit of negative feedback. Negative feedback meaning that as my base signal increases, and my collector signal also increases, some of that energy from the collector is fed back into the base. Remember, when this goes up, this goes down. So as this voltage goes up, some of that voltage comes through here and tends to drive the base voltage down. So it gives us some negative feedback, and that lowers the gain of the system and improves both the biasing and the distortion. Remember, the higher gain your amplifier, the more distortion you're going to get. And also it's distorted because as our signal comes through, the HFE is changing. I have a different HFE here than I do here. It distorts terribly. This will reduce some of that distortion. But then again, you look at books on small signal amplifiers and they say, here's an improvement, and then they move on because it doesn't really improve it that well. So this style of small signal amplifier, if you see it, it's going to be, if you see it at all, it's going to be very rare because they're just too fiddly, too dependent on the transistor. Tiny changes in temperature, everything else can throw this all off. So what do we do to make this a stable small signal amplifier? First of all, let's get this off of here, put it back where we had it. And what we're going to do is add a resistor here. What does that do for us? Let's get some of this clutter out of here. Well, what this does is it adds a significant amount of negative feedback to the system. What does that do? Well, it reduces the gain of the amplifier. We don't want to amplify too much in one stage because we're going to get distortion. We're going to get less frequency range, less bandwidth, more distortion. So we want to do it in stages and have only so much gain per stage. This is going to decrease the gain because it adds negative feedback. How does that happen? Well, remember that what happens here, as this voltage goes up, this voltage goes down. So they're always going in opposite directions. Well, what's happening? We have current flowing through the transistor. Now we have the opposite thing happening here. What happens when current encounters a resistance? Well, if I pull out my soda straw again, now we're going the opposite way. No current flow, same pressure on each side, but when I blow into it, I get a backup of pressure where the current goes in. So where conventional current enters the resistor, I get an increase in voltage. So what we have are two counteracting voltages here. My voltage is trying to go down here, but this voltage is trying to go up and push that voltage up. So that's negative feedback, and that greatly reduces the gain of the amplifier. So adding that emitter resistor reduces the gain of the system to where actually the gain is no longer dependent on the HFE of the transistor. The gain is reduced to such a point that the gain of the whole system is now, here's our collector resistor, here's our emitter resistor. Our gain is now our collector resistor divided by our emitter resistor. Transistor has nothing to do with it. So the biggest problem, which is the changes in HFE here with temperature, with current, with voltage, and different transistors, is eliminated. And now we have a nice stable circuit that's going to be easy to bias. And once we get it biased, changes here are not going to change the voltages. We can pull that transistor out and put almost any other transistor in, and everything's going to be the same because we're no longer dependent on the HFE of that transistor. And another thing that we do to improve this is add a little more negative feedback by making this a voltage divider. So what that does is, as current flows into the base, so some current that would have gone into the base goes into this resistor here, which means that we don't get as much current here, so we get there's less current to amplify. So this adds a little bit more negative feedback. Even more important, it stabilizes our voltage at this point because now it's more dependent on these resistors than it is on the characteristics of the base to emitter junction of the transistor. So this resistor makes our overall gain independent of the transistor, independent on the two resistors, and adding this resistor makes our base voltage more dependent on these two resistors than it is on the characteristics of the transistor. So there is our basic finished small signal amplifier. Let's erase it and redraw it just to declutter it a little bit here. And I'm going to eliminate the microphone just because I can. So there is our finished small signal amplifier. And once again, we're not talking about specific numbers here. That's beyond the scope of this lecture, but there are plenty of design manuals that can help you choose these resistors to design your amplifier if you should need to design one. Now let's look at another factor here. Is we're going to go into another stage here, and we have DC voltages here. We don't want to go that way. So what can we use to block the DC voltages that bias this up but allow the AC to go through? Of course, we're going to put another capacitor over here on the output, and that isolates the next stage from this stage. Now, there's one other improvement we can make if we want to. Now, the gain of the system is going to be this resistor divided by that resistor. However, what if we want a little more signal gain than the gain for our DC biasing? So our gain for our biasing that sets up what's this resistor, what's that resistor, what's the HFE of the transistor, getting everything balanced just right to get just the right voltage here and get everything to work. That's determined highly by these two resistors here, but also the gain of the whole amplifier. So if I have a gain of 2, let's say this is 1K and this is 500 ohms, which is a good starting point. This will have a gain of about 2. That means my amplifier is going to have a gain of about 2. What if I want considerably higher gain? The main reason we have less gain is because of adding this resistor. Is there any way to make our alternating current ignore this resistor where our direct current that sets up our biasing doesn't ignore it? Why don't we take another capacitor and bypass that resistor? So to alternating current, that's a short circuit. So as far as our signal is concerned, that's our circuit. So our gain is dependent on this resistor and the HFE of the transistor. So for our AC gain, we have a higher gain, but then for DC, that resistor is visible to the direct current. Let's put the bypass capacitor back in. So to alternating current, this resistor does not exist. So the gain is the HFE of the transistor combined with this resistor. But for DC, which cannot go through this capacitor, this resistor does exist, and the gain is this resistor divided by that resistor. So we increase our AC gain, our signal gain, by putting this bypass capacitor here. So that's the purpose of each one of these components. What does each component do? This component turns us into a voltage amplifier. So as our current changes through our transistor, we get voltage changes at the collector. This resistor biases our base. It brings up our base voltage so that it's high enough to operate the transistor. And then our alternating signal comes in, goes through this capacitor that blocks our DC from going that way, but allows the AC to come through. That causes our base voltage to go up and down, which causes our collector current to go up and down, which causes our collector voltage to go up and down. This resistor decreases our gain, so that all of the selections we make for resistors here are not dependent on the HFE of the transistor, because that's just too sensitive. It's just not going to work. So this resistor makes the gain of the system equal to this resistor divided by that resistor, making it a lot easier to set this up and get it stable. And then finally this resistor adds a little more negative feedback and also makes the voltage at the base of the transistor less dependent on the characteristics of the transistor. And finally this capacitor blocks our DC from going to the next stage but allows the AC to go through. So that's the basics of a small signal amplifier. Now that we've seen the typical small signal amplifier, let's take a closer look. Now in reality, as an electronics technician, you're much more likely to be troubleshooting one of these that someone else built than you are to build one yourself. As a matter of fact, if I'm going to build a small amplifier, I'm probably going to use an op-amp. It's just so much easier. But let's go ahead and build one of these and see how that can be done, and let's see how to troubleshoot it if something goes wrong. Now there are some formulas we can use to design this down to the T, but for a quick and dirty amplifier, if we're not too worried about the input impedance, we can design it pretty quickly without going through a lot of mathematics. And since engineering is beyond the scope of this class, we will do this with as little mathematics as possible. So what I'm going to do is design a small signal amplifier with a gain of 2. Let's get this out of the way for the time being. And remember that the gain of the amplifier is going to be this resistor divided by that resistor. So we have 1K here. Let's put 500 ohms here. Well, I have some 510 ohm resistors, so let's make that 510 ohms. And for the power, for experimental purposes, I just used a 9-volt battery that was actually a little weak down to 8 volts. So let's go ahead and just make this plus 8 volts. Nice even number. So we've got those two resistors. We have this resistor. I'm going to use a 2N2222. And how are we going to choose these two resistors? Well, it's fairly easy if you want to make a quick and dirty amplifier and trying to avoid the calculations. We want this resistor to be fairly big compared to this one, maybe at least about 10 times as big. So let's start by using a 20K potentiometer in place of these two resistors. And let's get this out of the way just for uncluttering the board here. And we already know what that is, so we get that out of the way. So here's a simple amplifier. We've eliminated our capacitors, and we've replaced those with a 20K resistor. All we have to do now is power this up and put a DC voltmeter right there and start turning this until what? Remember that we want the quiescent voltage, in other words the voltage with no signal input, to be 1/2 of our power supply voltage. That way our input can swing it all the way up to 8 volts or all the way down to 0 volts without hitting the limits. We cannot go above 8 volts, we can't go down below 0 volts, and if we hit those limits we get clipping distortion. So we don't want that to be, we don't want our sine wave flattened out at the top or the bottom. So to make it symmetrical, to give us the room to go either way as much as possible, we want to make this voltage 1/2 of our maximum voltage. So all we do is crank this potentiometer until we see 4 volts there. Easy peasy. Now let's take a look at what we've got. If we look at the rest of the circuit with the voltmeter, we would see that we probably have about 2 volts here and expect about 2.7 volts there. So it's 7/10 of a volt above the base. So the base is 7/10 of a volt above the emitter, and pretty much like we expect. Now what we want to do, just to find out what these resistors are, is simply measure this. And when I did this, I came up with, let's put the resistors back there. $13K and $7K. Now let's put an input on here. Let's start by putting in a coupling capacitor. Because of what I had in my junk box and just off the top of my head, I made that a 2 microfarad capacitor. And I put an input of 2 volts peak to peak. So it peaked at plus 1 volt and negative peak of minus 1 volt. Now we put an oscilloscope probe at this end, and voila, I ended up with 4 volts peak to peak with the output inverted compared to the input, as we see in the in setup here. So quick, easy peasy, made a small signal amplifier with a gain of 2, and we're ready to move on. Now, we might want to put a bypass capacitor around this resistor, and that will increase the gain. And we want that to be a fairly big capacitor, several microfarads, maybe 10 to 20 to 30 microfarads. We want it to be big enough that it's a total short circuit to all the frequencies that you might be amplifying. But remember that if we do this, we're going to increase the gain, but as you increase the gain, you increase the distortion and you decrease the bandwidth. So we might not want to increase the gain. We've already got a gain of 2. That might be enough. If I reduce the size of this resistor, we'll increase our gains. We can get a gain of 3 or a gain of 4 fairly easily without having to deal with the extra gain we get from this capacitor. Remember, if we put the capacitor here, our gain is going to be proportional to our HFE, and it might go high enough that it's really too much gain. So we control our gain with these 2 resistors, and if we want lots and lots of gain, we can put this bypass capacitor in here, but I'm going to leave it out for now. Just leave this a nice gain of 2 amplifier. And there we have it. That'll work. We have a working amplifier. All we have to do is have a coupling capacitor to take it to the next stage, to Now remember, this capacitor blocks the DC bias voltages on this side from going to the next stage, just as this capacitor blocks the DC voltages from going to the input. And we have a ready-to-go small signal common emitter amplifier. Now let's redraw this circuit and take a look at some scenarios just in case things go wrong. And with some jump cut magic, there it is. I've eliminated the coupling capacitors and the resistances just to keep this uncluttered while we look at it. And here are the voltages we expect at the collector, at the emitter, and the base of the transistor. Now let's make some things go wrong. I'll put in some other voltages here and we'll try to guess what went wrong with the circuit. So let's say our amplifier, we look at our input, remember 1 volt peak to peak, but our output is something lower, so we have a loss. So we pull out our DC voltmeter and start looking around and we see, plus 6.5 volts on the emitter, 7.3 volts on the base, and 6.5 volts on the collector. So the same voltage on the collector and the emitter, DC voltages. And let's look at these voltages here, 6.5 to 7.3 volts. That means we have a difference of 0.8 volts from the base to the emitter of this transistor. So transistor's obviously bad, isn't it? Remember, don't start assuming your transistor's bad because your voltages don't add up. Is it possible to have 0.8 volts from the base to the emitter of this transistor? Remember, that's a forward bias diode. Can we get more than 0.7 volts? Of course we can. We've demonstrated that over and over. How would we get 0.8 volts here? Sounds like our base to emitter current is too high. What could cause our base to emitter current to be too high? Our base voltage is set by this voltage divider and is pretty stable, but the current is basically the current through this resistor here. And notice the high voltage here. It looks like there's something wrong with this voltage divider. This should be just about 2.7 volts. This should be about 2 volts. Something is going wrong here. As long as these two resistors are okay, this should be pretty close to 2.7 volts. I think there's something wrong with our bias resistors here. Which one is most likely bad? Well, we have a lot of extra current flowing in here, so I would suspect this resistor right here. And in fact, this is what we would get if this resistor were a short circuit. So if this resistor is shorted, we can expect a higher than expected base to emitter voltage, and notice all these voltages are higher over here. We have a signal coming through the transistor, but it is a loss. So high base to emitter voltage, base voltage too high. Start looking at your bias resistors here, and in this case, this resistor is shorted. Here the input looks normal, but our output looks half-wave rectified. What's happening is our voltage is somehow hitting its lower limit, whatever that is. That's going to depend on how much current we have, and it'd be pretty close to 0 volts. But we're obviously hitting the bottom. And look at this. This voltage is too low. It should be 4 volts. It's down to 3 volts. This voltage is just a little bit high, which means we have a higher than expected current flowing through here. So what could cause that? And also look over here, our voltage is a little high here, which looks like, once again, we have more current than expected flowing into the base, it looks like. And what's that going to do? The more current we have going into the base, it's going to increase our collector current. What happens to our collector voltage as we increase this current? That collector voltage will go down. So this voltage has gone down. It's gone down such, so now our quiescent voltage is too low, and when this hits the peak, we're hitting the bottom over here. So now our DC voltage here is too low, so we are able to go up far enough, but we can't go down because we hit that lowest voltage. So once again, I'm going to be suspecting something is going on over here because this voltage still should be pretty close to 2.7 volts no matter what happens anywhere else. So the last time this resistor was shorted, this resistor is open. And so it's not quite as dramatic. Why is it not as dramatic? So we still have a voltage divider here. Our current flows through this resistor, then through the base to emitter path of the transistor. And this resistor, even though it's only 510 ohms, that resistance is multiplied by the HFE of the transistor. So it's kind of a funny thing. If you look here, you see 500 ohms or 510 ohms. But if you look in the base, because the transistor acts like a magnifier, this looks like it's going to be much larger. So this resistor becomes a fairly big resistor compared to this one, and it pushes our voltage at the point of the voltage divider up. So what's happened here is we've lost this resistor. It's an open circuit. So once again, if this voltage isn't right over here, suspect there's a problem with these two resistors. Okay, in this scenario, our input looks normal, but our output is simply 8 volts DC. We look at our DC meter, 8 volts, put our oscilloscope on there, and we just see straight DC at 8 volts. So there's no output getting out of the transistor. Our input voltage looks like about what it should be, so I suspect that these are okay. That should be pretty close to 2.7 volts. Depending on what's going on, it might get just a little higher. We'll see that a little later. But that looks good, so we're good over here. What could cause this to be 8 volts? This voltage is the same as that voltage. It could be just a coincidence, but it looks like this resistor could be shorted. Or is it? What if this resistor is open? Well, notice we have 8 volts here and 8 volts here. Yeah, I wouldn't expect 8 volts here if this resistor was shorted, because we would have a large current flowing through the transistor and there would be some voltage across it. So we wouldn't have the same voltage here as here. Remember, if we have current flowing through a resistance, which a good resistor would be, we will have some voltage difference. So if we have 8 volts here with current flowing through the transistor, I would expect something lower than 8 volts here. So I think I see a situation where there's no current flowing from here to here because we have no voltage drop. We have resistance, and this has resistance too. A transistor does have resistance. It tends to change, but it does have resistance. But we have the same voltage everywhere. I suspect that this resistor is open. Also, what if we just have a broken connection? Broken lead, broken solder joint, or whatever, where we have no connection to that resistor. So this scenario, with the voltage the same all the way across the back, it's a good indication that we either have an open resistor or a broken connection from the transistor to the resistor. So now we have almost the same situation. The only difference is that the emitter of the transistor is at 0 volts. So what could cause that? Well, the first thing you might think of, well, if this resistor were a short circuit, we would have 0 volts on the emitter, but that would not cause this voltage to go up to plus 8 volts. In fact, if this was shorted, it would increase the gain of the amplifier. So these voltages might be messed up. This voltage will probably drop to a lower voltage, but I certainly wouldn't go up, and I certainly wouldn't be a DC output. I'd have a greater output. So this resistor is probably not shorted. What could be going on? Well, if the transistor were an open circuit, if the transistor were not here at all, yeah, no current, the output would be up at our positive 8 volts. No current through here, this would be 0 volts. And of course, this would be sitting at pretty close to 2.7 volts. Actually, it might be a little different. So if you see a slightly different voltage here, maybe just a little bit higher, not a lot higher, I would strongly suspect that the transistor was a short circuit. But let's say this isn't higher. It's exactly where we expected, especially if we've looked at this circuit and it's the exact voltage we saw when the circuit was working. Now I have a new suspicion, and that is that I simply have no connection to the base of the transistor. So there's no connection coming in here, so there's no DC bias voltage, no current going from the base to the emitter, no current running through this resistor, 0 volts. Likewise, there's no current flowing through here, no current flowing through the collector resistor, that would be 8 volts. So this could be a bad transistor, an open transistor, very likely. The only difference is if the transistor is open, this voltage might be slightly higher than you expect, but it might not be. So this is a case where if you see that the collector voltage is all the way up and the emitter voltage is all the way down and the base voltage looks normal, could be an open transistor or a bad connection to the base of the transistor. Okay, here's another interesting situation. And I think this one might be the most obvious of them all. I've got 2.7 volts here like I expect. Might be just a tad higher, which might be a indication of what's going on. But we have the same voltage here and the same voltage here. We have an input of 1 volt peak to peak and an output of 1 volt peak to peak. It looks to me like this transistor is a short circuit, or there's something shorted around it. Of course, watch for other possibilities shorting out the transistor, but that looks like we've got a short circuit in here, either a bad transistor or something touching it and shorting it out. Just another thing to say, because I've seen it and it looks weird, you need to watch out for it. Let's say that these two resistors are whacked somehow and we don't have the right bias voltage on the base, such that this voltage drops down and starts to clip on the bottom as we showed. So we have a normal looking input, but our output looks something more like, well, let's draw our sine wave here and clip off the bottom. And this is sort of what we expect when we get clipping. But what you might get is a little bit of a bounce up when it hits bottom and it tries to go below 0 volts or below its lowest possible voltage because of the characteristic of a transistor and the saturation voltage. When you start going into saturation, the voltage might start to rise. And here's what we have here. So it starts to go into saturation, actually tries to go deeper into saturation, and the voltage actually comes up. And so instead of seeing it flat on the bottom, you see these little humps. So that's another symptom of out of whack bias resistors here, and the voltage here has gone down, and now we are clipping on the bottom going into saturation. If this gets bad enough, we can get something that looks sort of like kind of a weird wave shape. We have a long pulse, short pulse, long pulse, short pulse. So once again, this is happening because it's trying to go into saturation here, and as it goes deeper into saturation, the saturation voltage goes higher and gives us these little bumps here. And in fact, if you go far enough, this will eventually get to where the output is the same as the input, and we no longer have the inversion. It's no longer 180 degrees out of phase, and we end up with the output being the same as the input if we get these out of whack far enough. Just pointing that out, that if you see something really weird like this, it's trying to go into saturation, so it's trying to flatten the bottoms, but as it goes deeper into saturation, that voltage actually comes up, and so we don't have the flat bottoms there. So just something to watch out for so it doesn't throw you for a loop saying, what the heck's going on here? Well, transistors trying to bottom out, clip on the bottom and go into saturation, but that voltage tends to bounce back up because of the characteristic of a transistor. If you found this video useful and informative, please give me a thumbs up down below. It really helps the channel. And subscribe, because that not only informs you when I put new videos up, but it really helps the channel also. And a big thank you to my patrons at Patreon. I could not make these videos without your support. If you want to help me put these videos online and keep real vocational education free at vocademy.net, you can go to patreon.com/join/vocademy and pledge your support. And again, a big thank you to my patrons who make this possible, and a big thank you to everyone for watching.